Hi everyone. This is a video on determinants and Cramer's rule. Cramer's rule is a method for solving systems of linear equations. So we're going to learn determinants, that's part of it, and it won't mean anything at first, but it's part of a process for solving a system. Okay, so this is what a determinant looks like, kind of like an absolute value. And we have numbers inside. It's going to represent numbers from two equations in this case. Okay, and what we do with those numbers is we multiply the diagonal. So if we read this diagonal by rows, A, B, C, D, we're going to multiply A times D and then subtract B times C. So you're multiplying the diagonal and then subtracting the other diagonal going backwards. Kind of think of it that way. All right, let's do our first problem. Here's our first problem, 3, 4, 2, 5. So our first step is to multiply the diagonal. So that's 3 times 5. Put that down. And then we're going to subtract the diagonal going backwards, starting with the 4 times 2. So minus 4 times 2. And then work that out. So 3 times 5 is 15 minus 8. Okay, I know it doesn't mean anything right now, but it'll make a little more sense in a little while. So 15 minus 8 is 7. Well, let's try a couple more. Okay, so multiply the first diagonal. That's 4 times negative 3. And then minus the second diagonal going backwards, 2 times negative 7. 2 times negative 7 is negative 14, but there's a minus sign, so it's going to turn into a plus 14, right? So 4 times negative 3 is negative 12, and then it'll be plus 14. All right, we can do that multiplication in our head, so next time let's not write down all those steps. Let's just go ahead and go right to, like in the last problem, the negative 12 plus 14. Think of it as when you go backwards, you just change the sign. All right, let's do this next one. 5 times negative 2. 5 times negative 2 is negative 10, right? Now let's go backwards. Negative 4 times 2. What's negative 4 times 2? That's negative 8, right? But we're going to change the sign because there's a minus sign there, so we're going to put plus 8. Okay, and that answer would be negative 2. All right, remember to always pause and try to work out on your own. All right, let's see this first one. Negative 3 times negative 7, so we're multiplying the diagonal. And what does that give us? 21. So we don't change the sign on that one. Whatever you get, that's the sign you keep. And then we go backwards. We're going to change the sign. 2 times 5 is 10, positive 10, but we're going to put minus 10. And that gives us 11. All right, multiply the first diagonal. That gives us negative 6. Multiply the diagonal going backwards. That's a positive 21. Negative 7 times negative 3 is positive 21, but we're going to put minus 21. So that gives us negative 27. Cool? Okay. Now, those previous problems they're called 2 by 2 determinants, 2 rows, 2 columns. Now we're going to talk about 3 by 3 determinants. 3 rows, 3 columns. It gets a little messy, but we could do it. This is called the method that I'm showing is called the cross multiplication method. There's another method called expansion by minors. So in this video, I'm just going to use one method. I think it's easier. It's called cross multiplication. But if you're going to go on into linear algebra, then you might want to learn the expansion by minors. Okay, so here's our notes. The first thing we're going to do is we're going to rewrite the first 2 columns to the right of the 3 by 3 determinant. So whatever the first 2 columns are, you're going to recopy them to the right. And then this time, we're going to have not one diagonal, but 3 diagonals, starting with the first number on the top row to the third number on the top row. And whatever sign you get for those diagonals, you're going to keep them. And then we're going to subtract the 3 diagonals going backwards, starting from the 5th number on the top row to the 3rd number on the top row. So when we go backwards, we change the sign, right? Just like we did last time. We're still going to change the sign. Okay, and then we're going to add those 6 diagonals. So whatever we get, that's going to be the value of the determinant. Okay, here we go. So the first thing we're going to do is recopy it and recopy the first 2 columns to the right. There it is. So keep the first 3 columns just the way it is. But then the next 2, so now we have a total of 5 columns. We just recopy them to the right. So our 4th column is 2, 3, negative 1. And our 5th column is 5, negative 2, 1. All right, now we start with our first 3 diagonals. Excuse me. So start with the 2 at the top row. The first number on the top row in the first column, that's our first diagonal. There it is. And that gives us negative 12. 2 times 2 times 3 is 12, and it's a negative because that 2 in the middle is a negative, so it's negative 12. Let's go to the next diagonal. That'll give us negative 30. Okay, you get the idea? What's our next diagonal going to be? We're going to start with a 4. So it's going to be 4, 3, 1. And that gives us a positive 12. Now we're going to start from that 5 on the far right, the 5th column, and we're going to get our next 3 diagonals going backwards. We need to subtract those numbers, so whatever sign you get, you change it. If you get a positive value, put a negative. If you get a negative value, put a positive. All right, so 5 times 3 times 3, what does that give us? 45, right? But you're going to put negative 45. You got to change the sign. How about the next one? Two times 6 times 1. That'll give us 12, but you're going to put minus 12. And sometimes it's kind of hard to see. I try to put those little ovals around it to make it clear what we're doing, but then it gets a little messy. All right, 4 times negative 2 times negative 1. That's a positive 8, so we're going to put negative 8. And now we add that all up together, and hopefully we get negative 95. All right, let's try another. Okay, you could always pause and try to work it out. We're going to get started. Recopy the first 2 columns. And start getting your diagonals, starting with a 5 on the top row. negative 30. I put a plus 0. 0 is neither positive or negative, so it doesn't really matter, but I just put plus 0. Plus 0. 0 times 1 times negative 2 is still 0. And then the last one will be plus 12. Now we go backwards, starting from that 0, and whatever sign you get, you're going to change it. Well, again, 0 times anything is 0, so it doesn't matter whether you put plus 0 or minus 0, it's still 0. Next one will be 5, but we're going to put minus 5. And the last one will be negative 16, but we're going to put plus 16. Add that all up together, you should get negative 7. Okay, here's the punchline. I said it was a method for solving a system of equations. It's kind of like how a calculator would work. A calculator would just take steps to work out, and that's what this is. There's no thinking, oh, I should multiply this row by 3 and this row by negative 7. A calculator doesn't work that way. A calculator works on a list of instructions, and that's what this is. It's a list of instructions. So if we have a system, this is for a 2 by 2, and I noticed that we used subscripts. They're just so that you could tell which letter is different from another. So A1x plus B1y plus C1. A1, B1, and C1 are just numbers. And then we have A2x plus B2y equals C2. We're going to calculate 3 determinants. The first determinant we'll call D, and it's the coefficients of the x and y. So I'm reading by columns, A1, A2, and B1, B2. Now dx, notice I used the letters C1 and C2. C1 and C2 are those numbers that are constants on the right side of the equal sign. So C1 and C2 are in the first column. They actually replace the x coefficients from the D. And in the y column is still the y coefficients. Okay, now we have our third determinant, dy. And in the x column, so the first column is the x column, the second column is the y column. But in the y column of dy, C1 and C2 replace the y coefficients. Okay, so it is hard to memorize this, so that's why you want to recognize the patterns. In dx, the constants replace the x column. In dy, the constants replace the y column. And then finally, we could get our answers. X is equal to dx over d, and y is equal to dy over d. Kind of like how a calculator would work, right? It gets these numbers, and then it divides it, and it's done. It doesn't think about how to multiply rows or anything like that. Okay, so then we have this final note. If d equals 0, so you've been always thinking, well, when the denominator is 0, it's no solution, right? Well, we have two situations. It could either be no solution, which is inconsistent, or it could be infinitely many solutions, which is called dependent. If they're all 0, it's infinitely many solutions. But if d is 0 and one of them is not 0, dx or dy is not 0, then it's no solution. Okay, so if you get d equals 0, you can't stop. You have to keep going. You have to either show that all of them are 0 for infinite solutions, or as soon as you get one of them that's not 0, then you could stop and say no solution. All right, here we go. Let's do it. Here's our first problem. Notice that it's already written in ax plus by equals c form. So we have to have the x first and the y first, the y second, and then the constant on the right hand side. If it's not in that form, then you have to put it in that form. Notice there are no fractions. If you do have fractions, you have to get rid of fractions by clearing them. You clear fractions by multiplying the equation by the LCM or LCD. Okay, so let's find d, dx, and dy. Our d is going to be 2, 1. I'm reading it by columns. 2, 1, 3, negative 3. So d is the coefficients of the x, and then the coefficients of the y, reading by columns. And when we dx, the 2 and the 10 are going to replace the x column. So there's dx, 2, 10, and then the y column, 3, negative 3. And when we do dy, the 2 and 10 are going to replace the y column, but the x column will stay what it was in d. So for dy is 2, 1, 2, 10. Okay, now I'm not going to write down all the steps for the diagonals and what we get. I'm just going to put the answers. You know how to work that out. So for d, you should get negative 9. dx, negative 36. And dy, 18. Now we can use those equations. X is dx over d, and y equals dy over d. So dx over d is, well, dx is negative 36, and d is negative 9, which equals 4. Okay, now let's do dy. Y is dy over d. dy is 18, and d is negative 9, which is negative 2. So we got our answers. 4, negative 2 is our final solution. All right, let's try another. Again, you should pause it and try to work it out. All right, so d is 5, 2, 4, negative 3. That's the x column and then the y column. Now when we do dx, the x column gets replaced by those constants on the right hand side. So negative 32, 1 replaces the x column, and the y column stays the same. Then when we do dy, the x column stays the same, but the y column is replaced by the constants. Okay, now work out each of your determinants. All right, d is negative 23, dx is 92, and dy is 69. X is dx over d, and y is dy over d. So x equals 92 over negative 23, which turns out to be negative 4. And y equals dy over d, which is negative 3. So there's your answer. Negative 4, negative 3. Just following the steps. Not terribly complicated. Just a little tedious. Okay, let's do one more with 2 variables before we tackle problems with 3 variables. All right, let's first do d, dx, and dy. D is 1, 2, 3, 6. Reading by columns. Dx, the negative 5, 1 replaces the x column. And in dy, the negative 5, 1 replaces the y column. All right, let's do d first. Oh, d is 0. Yeah, that's right. 6 minus 6 would be 0. Okay, that means we cannot stop. We have to keep going. There's two options here. It's either no solution or infinite solutions. If we get them all to be 0, it's infinite solutions. But as soon as we see that one is not 0, then we could say no solution. So let's do the next one. What do we get? Negative 33. That means it's no solution. I don't need to worry about dy. It may be 0, it may not be 0, doesn't matter. As soon as we find one of them that's not 0, we could stop and say no solution. If we would have got dx to be 0, then we would still have to keep going. And maybe dy is 0, maybe it's not, but we would have to keep going. Okay? Here we go. 3 variables, 3 unknowns, x, y, and z. It's very similar to the 2x2s that we just did. This time we have d, dx, dy, and dz. Again, notice the patterns. In d is the coefficients of x, y, and z. But those constants on the right, d1, d2, and d3, in dx, it replaces the x column. In dy, it replaces the y column. And in dz, yeah, you guessed it, it replaces the z column. And then the punchline is x equals dx over d, y equals dy over d, and z equals dz over d. Same note as last time. If d equals 0, we got to keep going. If one of them, if dx, dy, or dz does not equal 0, then it's inconsistent. The solution is no solution. If they're all 0, if d, dx, dy, and dz are all zeros, then the equations are dependent and there's infinitely many solutions. All right, let's do one. It's a little bit of work, so I'll probably only do one. All right. Write it all down. See if you can tackle what d, dx, dy, and dz. Again, I won't show all the work here, but we'll set it up. So there's d, reading by columns 1, 1, 2, 1, negative 2, negative 1, and the z column is 1, negative 1, negative 2. Now when we do dx, the 4, 1, negative 1 is going to replace the x column. And when we do dy, the 4, 1, negative 1 is going to replace the y column. And then when we do dz, it's going to replace the z column. Okay, so there it is. There's dx, replacing the x column. There's dy, again it's replacing the y column. And then there's dz, now it's replacing the z column. I know, it is a lot of work. Yes, you're absolutely correct. Math is a lot of work. It's always going to be a lot of work. We kind of enjoy it, right? Yeah, we do. Okay, there's our d, which is 6. Again, I'm not showing all the work. There's our dx, there's our dy, and there's our dz. And we go right to the punchline, right? X is dx over d, y is dy over d, and z is dz over d. So you should get 2, -1, 3. All right, I know I didn't show a lot of the steps on that problem, but it would take up too much space, and we'd have to use multiple slides. It would be kind of messy. Anyways, good luck, and I'll see you here for the next video.